Welcome to my presentation on the topic Tough and Damage-Tolerant Composites for Biaxial Loading. A variation of material properties is an effective method to increase the fracture toughness by using the material inhomogeneity effect. Numerous works in the past have addressed the problem of a crack subjected to uniaxial tensile load approaching a perpendicular material inhomogeneity, as seen in figure A to D. A disadvantage of the composite geometries in A to D is that they are only applicable to uniaxial loading conditions, as they do not provide sufficient stiffness normal to the load direction or would fail due to delamination under biaxial loading. The motivation of my work is to develop a fracture-resistant composite geometry that is suitable for biaxial loading conditions, as it is of more practical relevance for engineering applications. One idea could be to insert interrupted interlayers as seen in figure E, which form isolated inhomogeneities within a material matrix material. To further improve the interlayer pieces, they could be formed into elliptical or spherical regions in order to minimize the stress concentration, as shown in figure F. To maximize the inhomogeneity effect, holes can be used as inhomogeneous structures. The most effective way to improve the fracture toughness is to trap an approaching crack so that it has to reinitiate again. Therefore, it is required to predict the crack path to decide if a crack is getting arrested or will continue to propagate. In this presentation, I will focus on the effect of a single circular hole to solve two important problems: predicting the crack path to decide if a crack gets trapped by using a configurational force concept, and determining the improvement in fracture toughness of arrested cracks by a damage-based approach. The configurational force is based on the work of Eshelby and describes a thermodynamical driving force on a defect. The configurational force F is defined as the divergence of the energy-momentum tensor C. As we consider a crack to be a defect within a material, the configurational force F tip at the crack tip can be considered as physical crack driving force. The direction of the crack driving force is defined by the second law of thermodynamics, implying that any physical process occurs in such a way that the dissipation of the whole body becomes a maximum. Therefore, the criterion states that the crack will propagate into the direction of the negative crack driving force vector. The configurational force at the crack tip can also be related to the near tip J integral J tip, which corresponds to Rice's near tip J integral and identifies J tip as the crack driving force vector pointing in the direction of crack propagation. The crack driving force vector J tip is calculated by the sum of the far field J integral vector J far and the material inhomogeneity term vector C inhomogeneity. The far field J integral vector can be obtained by integrating the configurational forces along a contour gamma far along the external boundary, including the crack faces, but excluding the crack tip. The material inhomogeneity vector C inhomogeneity can be obtained by integrating the configurational forces along the boundary of the hole. The procedure to predict the crack path in the vicinity of a hole consists of three steps. At first, a two-dimensional plane-strain finite element model is used to determine the equilibrium stress and strain fields of a straight crack and a circular hole. The material behavior is kept linear elastic. The crack length is kept fixed, while the position of the hole is varied relative to the crack tip in horizontal and vertical direction. The investigation includes surface cracks, as seen in the model, and internal cracks, where the symmetry boundary condition is applied on the left boundary of the model. Three loading conditions were investigated: uniaxial loading, beta being 0, biaxial tensile loading, beta being 1, and biaxial tensile compression loading, with beta being -1. The second step is a post-processing procedure developed by Marko Kegel at the University of Maribor, which was developed to calculate the configurational force distribution as well as the contour integrals J-far, C homogeneity, and J-tip. The post-processing tool requires the equilibrium stresses and strains, the elastic strain energy density, and the contours gamma far and gamma epsilon. Figure A to C show the finite element mesh with the configurational force distribution on each node. Figure B shows the distribution of the configurational forces along the whole boundary, and the dominant configurational force F-tip at the crack tip. A closer look at the crack tip, as seen in figure C, reveals that the additional configurational forces appear close to the crack tip. These bulk configurational forces ahead of the tip are not realistic. They result due to discretization. This indicates that F-tip alone do not describe the crack driving force accurately. To determine the crack path, we need the correct propagation angle alpha tip of each calculated j-tip vector. The two-dimensional distribution of the correct propagation angle is shown below the abscissa in the figure. The crack is assumed to approach from the negative side. Red areas indicate that j-tip vector is pointing towards the hole, and blue areas imply that the j-tip vector is pointing away from the hole. Therefore, a significant crack deflection is expected primarily when the crack is close to the hole boundary. The maximum crack deflection appears under an angle of approximately 80 degrees from the symmetry line. To evaluate the deviation of crack driving force along the crack path, the magnitude of the j-tip vector is normalized by the j homogeneous and equals s-tip as seen in the figure above the abscissa. The normalization factor j homogeneous is the magnitude of the crack driving force vector in the homogeneous material with the same crack length, same material properties, and loading conditions. The red areas indicate an increase and the blue area a decrease in the crack driving force compared to the crack in the homogeneous material. The maximum decrease of the crack driving force appears at about 115 degrees from the symmetry line. The area where the crack driving force deviates more than 10% from the homogeneous case is defined as interaction area AI, and the area where the crack propagation angle deviates more than 5 degrees from the horizontal direction is defined as deflection area AD. These definitions are arbitrary, but it helps to understand how holes can be arranged in relation to each other to optimize their effect. In the third step, an interpolation procedure uses the two-dimensional dataset of the crack propagation angle and the normalized crack driving force to determine the crack path and the crack driving force along the path. The interpolation procedure is developed in Python using a scientific Python library. The procedure uses a quick-call algorithm, which is an n-dimensional algorithm for data interpolation. The interpolation scheme requires three input parameters: the initial starting point of the crack extension increment delta A, and the trapping criterion. Once the dataset is generated, the interpolation method is very fast in predicting the crack path. It is several orders of magnitude faster than extended finite element method or conventional crack extension techniques. A crack trapping criterion is needed to decide whether the crack gets arrested or not. As shown in figure B, it is assumed that a circle with a radius RC defines the region where a crack is absorbed by the hole. The radius RC represents the radius of a circle with a 20% larger cross-section than the geometric hole. To assess the ability of holes to attract cracks under certain boundary and loading conditions, the aim is to determine the trapping zone size for each configuration. The trapping zone is defined by the farthest crack path from the hole center that gets arrested at the hole and stopped from further propagation. The trapping zone is measured at the beginning of the interpolation zone. The size of the interpolation zone is roughly defined where the normalized crack driving force S-tip is in the range of 2% compared to the homogeneous case. At this distance, crack deflection does not yet occur. On this slide, you can see the results of a surface crack interacting with a hole under uniaxial and biaxial loading conditions. Figure A and B show comparison between the interaction areas and deflection areas of three considered loading conditions. Noticeable here is the large shielding area AI- in figure A for the biaxial loading condition beta equals -1. The largest attraction area AD+, which is an indication for crack attraction, appears for the biaxial tensile load case where beta equals 1. Figure C shows the crack paths in the vicinity of a hole, and figure D the normalized crack driving force along the crack paths in C. The paths at A start at a vertical distance of Ly to R is 1, and as they approach closer to the boundary, the crack driving force increases strongly compared to the homogeneous case. Anyway, these cracks are not dangerous as they get trapped by the hole. The cracks paths at B indicating the farthest approaching cracks that get arrested by the hole, and therefore they define the trapping zone size, here defined as lambda trap, which is the trapping zone size normalized by the hole radius R. The most effective crack trapping appears for a surface crack subjected to biaxial tensile loading, where beta equals 1 with lambda equals 2.1. The weakest attraction appears for an internal crack subjected to biaxial tensile compression loading, where beta equals -1 with lambda equals 1.35. The improvement in the fracture toughness of an arrested crack is modeled with a damage-based approach. A symmetric arrangement of crack and hole is assumed as shown in Figure A. We will consider two cases, a crack reinitiation from a flawless hole, as shown in Figure B, and from a hole with a pre-existing defect on its surface, as presented in Figure C. For the case with defect, a worst-case scenario is assumed for the position of the defect. The defect is located at the boundary of the hole and oriented in horizontal direction. Figure D represents the reference configuration of a crack in the homogeneous material. The crack in the reference configuration as well as the defect at the hole are modeled as a rectangular notch of one element size. The fracture behavior is modeled by a damage-based approach, the so-called ductile damage plasticity model, as seen in Figure E. After damage initiation at point 2, stiffness and strength of the material are decreased linearly to 0, down to point 3. Damage evolution is controlled by a specific fracture energy, GF. Fracture is described by element deletion when the damage variable within an element reaches the point of failure at point 3. The used material parameters for the damage model are listed in the square box. The improvement in the fracture toughness is determined by evaluating the global failure stress sigma f of the specimen. The global failure stress sigma f is defined as the maximum applied stress sigma infinity at which the specimen fractures. The results in Figure A compare the failure stress for different boundary conditions and loading conditions. For long cracks, the bi-axiality factor beta has no influence on the failure stress sigma f. Differences between the different loading conditions appear for shorter cracks. The failure stress for trapped internal cracks is higher than for trapped surface cracks. Figure B relates the failure stress of uniaxial loaded surface cracks to the reference configuration. It can be seen that the damage-based approach fails to predict the improvement in fracture toughness compared to the homogeneous case. It is seen that the parameter sigma f to sigma f reference is strongly mesh-dependent. Figure C shows the improvement of trapped cracks with defect size of 1 micron compared to the homogeneous case. Sigma f to sigma f reference is no longer mesh-dependent as long as the defect at the hole and the crack of the reference configuration have the same crack tip notch size. For long cracks, the fracture toughness improvement is similar for all loading conditions. The fracture toughness is approximately 9.5 times higher with a defect on the boundary than for a crack in the homogeneous material. Figure D shows the effect of the normalized defect size on the fracture toughness improvement. With increasing defect size, the improvement decreases rapidly. At a defect size of 1% of the hole radius, the improvement decreases to a value of 4. Is the defect size in the order of the hole radius, the shielding effect of the hole disappears. Same distributions appear for uniaxial and biaxial loading conditions. Summing up the most important statements from the presentation. A computationally efficient interpolation procedure was presented to approximate the crack path. The crack attraction by a hole depends on A, the boundary condition, and B, the loading condition. The most effective attraction appears for surface crack under biaxial tensile load, and the weakest attraction appears for an internal crack subjected to biaxial tensile compression loading. For a perfect hole, no accurate predictions can be made on the improvement of the fracture toughness without any calibration. For an imperfect hole with a defect size of 1 per mil of the hole size, the fracture toughness increases by a factor of 9.5 compared to the homogeneous material. The improvement of imperfect holes is strongly dependent on the secondary defect size. I'm at the end of my presentation and thank you for your attention.